Hi, everyone. We're going to go ahead and get started in just a few minutes. Good afternoon. Thank you for joining us on our call today. My name is Katerina Oos from Transcat, and I'll be your moderator this afternoon. Our webinar topic is Tools and Techniques for Commissioning and Maintaining PV Systems. This topic is being presented by Will White from Fluke. Will has worked in the renewable energy industry since 2005, first as an installer for a small east solar integrator, then added sales, design, and project management to his skill set. In 2016, he joined the curriculum team at Solar Energy International and focused on updating and developing course content and teaching in person and online for 5 years. His last role was Director of Business Development, helping clients identify training opportunities. In 2022, Will joined Fluke as a solar application specialist, where he supports their renewable energy testing equipment like IV curve tracers, electrical meters, and thermal imaging cameras. We expect today's presentation to last roughly 60 minutes, and then we'll answer any questions that have been submitted. During any time of the presentation, you can send questions through the question box to the right in your webinar controls. I also want to mention that this webinar is being recorded. Each of you will receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. Attendance for the live seminar qualifies for an NABCEP education credit. Please stay for the duration of the webinar if you would like to receive a certificate of completion. Please reach out to me via email. At this time, I'm going to turn the presentation over to Will.
Thanks, Katerina. Will White from Fluke here. Today we are going to be talking about category ratings of test equipment and how that applies to how it's used in solar. We'll also look at voltage along with category ratings so we can make sure that you're choosing the appropriate test equipment for the type of work that you're doing. We'll do a quick review of IEC 62446-1, which is the testing of grid-connected photovoltaic systems. But we're going to spend most of our time looking at the solar workflow from installation through commissioning and operations and maintenance, and looking at all the tests that are done at each stage of the process. When we're looking at selecting our test and measurement equipment and making sure it's properly rated, the first thing we need to learn about is transient voltage spikes. Transient voltage is a momentary spike in voltage that we're not looking for. In the solar industry, it's typically coming from the utility, either from an issue in the utility like load switching or an equipment malfunction. If we have a system that is connected in a commercial building, we could have motors turning on and off, which might be causing voltage, transient voltage spikes. And then on the DC side, lightning can cause transient voltage spikes. They're invisible to normal multimeters and clamp meters. We do have at Fluke power quality analyzers that are capable of logging transient voltage spikes if it's a consistent issue that you need to troubleshoot. They're very short duration, but they can be very dangerous. And what happens is if you're testing voltage when a transient voltage spike occurs, if your tool is not properly rated, it may overwhelm the tool. It may damage the tool. It could cause a safety hazard to the technician using the tool. So we need to make sure that the tool is designed to withstand these transient voltage spikes without causing a potential safety issue to the technician. Now we do this through category ratings. There are 4 categories of electrical equipment, 1 through 4. The higher the category rating, the more potential there is for larger transient voltage spikes. So when you look at these systems, and our solar arrays, according to this IEC standard, are considered a category 3 environment, unlike our branch circuits in our house, which would be considered category 2 environments. We also have a category 4 environment where we get closer to the utility. That would be our point of interconnection with our PV array. If you're on the utility scale projects, between the inverter and the medium voltage transformer would be considered category 4 environments. When we rate our test equipment, the higher the voltage is of the system we're working on and the closer we are to the potential source of transient voltage spikes, the larger the safety requirements of that tool would be. When we're looking at category ratings, a category 3 tool will have a higher transient voltage spike resistance than a category 2 tool, category 4 higher resistance than category 3 rating tools. So we need to know what environment we're working in solar. If you're working on a PV array, that's category 3 environment. If you're working on the electrical system on the AC side, close to the utility, that's going to be a category 4 environment. Once we know the category ratings, we need to know the voltage of the system that we're going to be working on. In solar, we work on a wide range of voltages. We could be as low as 40 or 50 volts for a single module, up to 1500 volts for a string of modules. On the AC side, we could be doing 208, 240, 480, 600 volt, and even some utility scale inverters are operating at 800 volts now. So we need to have a test instrument that has a voltage rating higher than whatever voltage we'll be testing at. This last bullet on the screen right now is really important as well. You need to have the probes that are rated to match the meter that you're using. So if you're using, for example, the Fluke 393 clamp meter, which is a category 3 1500 volt meter. It comes with category 3 1500 volt test probes. But if those probes should become damaged and you need to replace them, category 3 1500 volt test probes are fairly uncommon. So it may be tempting to go into your toolbox and pull out whatever probes you have, but chances are they're not going to have that same category 3 1500 volt rating. And if you're working on a 1500 volt system, you may be introducing a point of failure into that test circuit. When we're looking at voltage ratings, we may have the same voltage of a tool, but if the category rating is different, the safety rating will be different. So in this example, a category 3 1000 volt test tool is designed to withstand 8000 volt transients, where a category 2 1000 volt test tool can only withstand 6000 volt transients. So even though they're both 1000 volt rated, because the category rating is different, the ability to withstand transient voltage spikes is also going to be different. Now, one thing that we run into in the test and measurement industry that I like to point out is that not all test tools that are designed to test up to a certain voltage are actually rated to that voltage. For example, you may see a test tool that is rated to test 1500 volts or even 2000 volts, but when you look at the rating, it's actually category 3 1000 volt rated or even 600 volt rated. And so it's not really designed to withstand those transient voltage spikes for that voltage that it's actually testing. Category ratings are usually very simple to find. On a Fluke tool, it's going to be printed right on the tool. This is an example of a multimeter that's category 3 1000 volt rated, category 4 600 volt rated. It is very common in almost every case. The category 3 voltage rating is going to be higher than the category 4 voltage rating because the susceptibility to transient voltage spikes is higher the closer you get to the utility. Now I want to point out a series of clamp meters that we have at Fluke. The smaller one on the left is the 325 clamp meter, that's category 3 600 volt rated. The middle one is the 378, that is category 3 1000 volt rated, and then the 393 on the right, which is category 3 1500 volt rated. And these photos are relatively to scale, so you can see as the voltage rating goes up, the tool gets larger. And that's because there's more space inside the higher voltage tools to create a larger safety barrier for the technician so that they're not at risk when they're doing testing on these systems. Now at Fluke, when we have our tools designed to a certain standard, we build it to that standard, but we also send it out to a third party to have it independently verified. They will take the tool, they'll test it to what the standard says it should be able to meet, and then they give the approval certification of that tool. Not all test instruments manufacturers do that. Some of them, quote unquote, design to the standard, but they don't actually have it third party tested. So there's no way to verify that it actually meets the requirements of that standard. As I mentioned, all Fluke tools are designed to the standard and independently tested by an agency like CSA or TUV, so we know that the tool actually meets the requirements of that standard. IEC 62446-1 is the requirement for testing grid-connected photovoltaic systems. This is a standard that is a legal requirement in many European countries, so they have to test to the standard and provide documentation that the tests were completed. Here in the US, where we don't have a required standard like this, we're not forced to use this standard, but it is a really good requirement of what tests we should be doing on our systems, and it's a good guideline to follow. This standard has two sets of testing. Category 1 are safety tests. This includes testing the continuity of the equipment grounding conductors and the grounding between the non-current carrying metal parts. So making sure our module frames are bonded to the racking, it's bonded to the equipment ground, things like that. We're going to test the polarity, open circuit voltage, and short circuit current of our PV circuits. We'll test our equipment functionality, make sure our disconnects work, our overcurrent protection devices are functional, make sure the inverters working properly. And finally, we'll do insulation resistance testing of all the DC circuits to make sure that the insulation was not compromised during the installation process. The second category of testing is for performance, and this is IV curve testing. So testing our modules and our strings of modules to ensure that they're operating properly and to find any potential defects there. There are many different steps in the solar life cycle. In this presentation, we're going to focus on installation, commissioning, and operations and maintenance because that's where all the test and measurement is done on these types of systems. In the installation phase, a really good test to perform is insulation resistance testing. We're doing this to make sure that the insulation of the wire was not compromised. We can also use this type of testing to identify ground faults, both during installation, at commissioning, and in operations and maintenance as well. What we're doing is essentially charging the wire. The wire needs to be disconnected from any other components, especially electrical components. We're going to send a high voltage, low current charge into that wire and see if there's any current leaking to ground. At Fluke, we have a wide range of insulation resistance testers from handheld meters like we see in the picture here, the 1587 and the 1507. Those will both test at 1000 volts. Not listed here is our new product, the 1537. That is capable of testing up to 2500 volts in 100 volt increments from 250 to 2500. That's an excellent product for 1500 volt utility scale systems where you need to do insulation resistance testing at 1500 volts, which is the recommendation of the IEC 62446-1 standard. The 1587, 1507, and the SMFT 1000 are not capable of testing above 1000 volts, so they're good for the lower voltage systems, but you really should be using something a little more higher voltage with the utility scale projects. The SMFT 1000 is a solar multifunction tool. It can do insulation resistance testing up to 1000 volts. It performs essentially every test that IEC standard recommends, and we'll see that as we go along through this presentation. Now at the commissioning stage, some very simple but critical tests are testing DC, open circuit voltage, and polarity. We're testing open circuit voltage to ensure that we connected the proper number of modules in series. If we get, well, first we need to calculate what our expected voltage is. Then if we see voltage that is too high, we know we connected too many modules in the circuit. If the voltage is too low, we connected too few, and those issues are typically paired together where one string is too high and one string is too low. Now, testing polarity is to make sure that we connected the positive connectors together and the negative conductors together. If we reverse polarity, we can create a closed circuit where current is flowing through the circuit, and that could cause damage and is a safety hazard. In this picture here, we have someone testing polarity in a combiner box. At the top here, we've got our negative conductors, which come in and to this bus bar, and then we've got all of our positive conductors, which come in through fuse holders and then are connected with this large bus bar in the middle there. If we do polarity testing at commissioning before we have closed the fuse holders, we can identify polarity issues before they become a problem. So if someone connected a positive and negative conductor to the positive bus bar, with the fuses open, that's an open circuit. They're not connected together. But as soon as I close those fuses, I've connected that positive and negative conductor together. I will have current flowing through that circuit. If someone should open that fuse holder under load like that, it will arc. It will damage the fuse holder. It's a safety hazard to the technician, and it may cause that fuse holder to melt, which will melt the fuse holders adjacent to it. It may cause a cascading catastrophic failure. Very important to test voltage and polarity at commissioning before the fuse holders are closed and the system is turned on. I want to point out this meter in the picture. This is the 393 clamp meter, specifically designed for the solar industry. when testing polarity in solar, it's very monotonous. You know, as this person in the picture here, you're out in the sunny weather, it's hot out, you get a bunch of personal protective equipment on. As they're going down this test box testing polarity, it can be very easy to miss the negative polarity symbol. With the 393 clamp meter, when you see the reverse polarity, it gives you the little negative sign. It says polarity on the screen. The entire screen lights up red, and the tool beeps at you. So it's basically impossible to miss a reverse polarity situation with this meter. The two AmProbe models that are listed on the slide are actually being discontinued because we are going to be releasing a Fluke 1500 volt category 3 rated multimeter, the 283. That will be coming out very shortly in the third quarter. That is capable of testing up to 1,500 volts, has the same polarity feature that the 393 has. It is also capable of testing AC voltage in category 4 environments up to 1,000 volts. So if you're working on utility scale projects where your inverter output circuit is operating at 800 volts, that 283 multimeter will be an excellent choice. The 393 clamp meter can test up to 1,000 volts in a category, 1,500 volts in a category 3 environment for our DC array. It can test up to 600 volts in a category 4 environment on the AC output side. The SMFT 1000, again, designed for all the IEC standard tests, can check voltage and polarity and can also save the results and report that information out later. Also at commissioning, we often do IV curve testing. This is to ensure that our modules and strings of modules are operating properly. We're going to create a historic record at commissioning and make sure that we can refer back to see that the system was working properly when we commissioned it. The nice thing about IV curve testing is you can often find problems with the system that would not be identified with voltage or current measurements. So the IV curve test gives us a full picture of the performance of the module or string modules. At Fluke, we have 3 models of IV curve tracers. The SMFT 1000 will test up to 1,000 volts and 20 amps. We actually have 2 versions of the Solmetric product, the PVA 1500T2 and the PVA 1500HE2. Those will both test up to 1,500 volts and 30 amps. And the big difference between the 3 models is how they work with high efficiency modules. Modules with high efficiency, the cells have high capacitance. And what that means is when we conduct an IV curve test, when it first starts, there's a large inrush current to the IV curve test tool. Some tools like the SMFT 1000, when you go above about 19%, will see that inrush current as an overload short circuit current and will stop the test from happening to prevent damage from that overload current. The PVA 1500T model, when the efficiency rating of the module is above 19%, the current rating drops from 30 amps down to 10. So that's to be able to deal with that inrush current and not overheat. The PVA 1500HE2 model is specifically designed for working with high efficiency modules. It can test up to the full 30 amp rating no matter what the efficiency of the module. So if you're working with high efficiency modules, that 1500HE2 model is really an ideal choice. Another test we do at commissioning is earth bond continuity testing. This is a measurement of resistance in ohms. We're checking the continuity between 2 points, and that could be any 2 non-current carrying metal parts like the module frame to the racking, between different racking sections or tables. It could be between the module and the ground rod. Any 2 metal points, we can test resistance. And in this case, we're really looking for low resistance. The IEC standard, I believe, calls for half an ohm resistance or less. So making sure all those metal parts are bonded together. And that's for safety, because if we have a ground fault, we want an easy path for that current to go to ground without that path being through our technician. If a technician touches a metal module frame that has a ground fault and that frame's not properly bonded to ground, the technician becomes the path to ground, and that's where electrocutions and shock hazards happen. There's a different IEC standard for this type of testing that requires a 200 milliamp test, which is a current level much greater than most multimeters are capable of doing. So we have the SMFT 1000 and the 1507 insulation resistance tester can both perform this type of a test at the 200 milliamp level. Important to make sure all those metal parts are bonded together. A related test is making sure that our ground rod actually has a good connection to the physical earth. There are several different tests we can do this. We're doing it for the same reason. We're testing our bonding between metal parts to make sure that there is a good path to ground. If we don't have good bonding, another issue we can run into is that overcurrent protection devices like circuit breakers may not work because they need that loop path to ground for that current to go through the ground into the breaker and trip the breaker. We have a suite of tools for doing this type of testing. The 1630 is pictured here, where it is a stakeless test that needs auxiliary ground rods to be able to conduct that test. The 1625-2 comes with some auxiliary ground rods, so that one can do multiple versions of that test in order to ensure that that ground rod has a solid connection to the earth. At commissioning, we also do performance testing. This is making sure that the actual output of our system meets our expectations. It can also be used to test the efficiency of the inverter, making sure our system's working right, setting a baseline for the future so that we know the system was operating right when we commissioned it. We have a couple tools that can do this. The primary one is the SMFT 1000, which is what these screens on this slide picture. The first one on the top right is measuring our DC power, so putting our voltage probes on and a current clamp around one of the DC conductors, measuring power. The SMFT will save that measurement. Then we can move our probes to the AC side, measure AC power, and it will automatically calculate our inverter efficiency. The limitations of the SMFT 1000 for this power measurement are the current clamp that comes with it is limited to 60 amps, so we can't test circuits above 60 amps. And in order to test the DC power, we need to get all of those current carrying conductors, the negatives in this case, into that clamp. So if we have an inverter with a large number of circuits, it's going to be kind of challenging to physically get it into that clamp. The 393 clamp meter and the upcoming 283 clamp multimeter, which comes with a wireless current clamp, also 60 amp rated, are capable of measuring DC power. You'd have to separately measure AC voltage and current, measure and calculate that power, and then calculate inverter efficiency for that to use that tool. Another technique that is used at commissioning and in operations and maintenance is thermal imaging. We can use handheld thermal imagers to look at things like really any piece of electrical equipment like disconnects, our combiner boxes, inverters, transformers, module interconnections, or fuse holders, overcurrent protection devices. On our modules, the most common type of thermography used on modules is aerial thermography. So using a drone with a thermal camera to fly over the array, see if there are any deviations in the temperature of the array. We can also use handheld thermography to look at the interconnection between modules to see if we can find high resistance connections there that might be arcing. When we're doing thermal imaging, we need to have the system operating at a high capacity. So we want a higher radiance so the system is working under load. That's what's going to give us temperature differentials that we can see using thermal imagers. Thermal imaging, unlike many of our other test tools, you can't just take it out of the box and go and take thermal images and expect to get good results. You really need to have some training to be able to get good pictures and good data. The big problem we run into in solar is you'll take a thermal image of a module, it will look like a hotspot, but actually it's just the reflection of the sun. So getting training will give you the information you need to avoid issues like that. When we're doing thermal imaging, we can look for things that are hotter than they should be or hotter than similar components. We can also look for components that are cooler than similar components. In this picture here, we've got several circuits in this box. The one on the right is cooler than all the rest of them. That's because there's no circuit connected to that component. So obviously it's going to be cooler than the rest of the components that are operating. If this was a combiner box and we saw a fuse holder that was cooler than the other fuse holders, we'd know that that circuit is not operating properly. There's probably an open connection somewhere in the circuit. At commissioning, we can use this thermal imaging data to set a baseline to see how things change in the future. I will say, when we're doing thermal imaging in solar, we're not usually looking for a specific temperature. We're looking for more quantitative data to see how things compare to each other. Fluke has a whole line of thermal cameras. There are drone-based cameras out there. Fluke does not have a drone-based camera at this point. We have a line of handheld cameras starting from the small PTI 120, which is about the size of a cell phone. We have a new small entry-level thermal camera coming out called the IC, and that will attach to a smartphone and use an app to take the pictures. Actually has a higher resolution than the PTI 120 at a much lower cost, so that's going to be a good option. And then we have a range going there from fairly relatively inexpensive cameras up to the highest end, the TI 480 Pro. As you go up in the camera range, the ability to take a high resolution photo increases. So the higher the resolution goes, the further you can be away from the component and still get good quality images. So if I have a high resolution camera, I can be outside the electrical hazard zone or arc flash zone of the equipment and still get a good thermal image. The TI 480 Pro also has interchangeable lenses, so I can add a telephoto or a wide angle lens to that camera as well. Now, something that's often overlooked in operations and maintenance is a simple visual inspection, walking around to see if there's any issues with the system. We can often find things that are easy to spot, like burnt out module interconnections, damage to modules like cracked glass or damaged cells, burnt out interconnections within the module. To do a good visual inspection, you really need someone who is trained to look at these systems and see what damage there is. Having a checklist helps as well. This is a picture from the SMFT 1000. It has a built-in checklist based on that IEC standard. That standard has a whole list of items that need to be visually inspected before you do any physical tests. With the SMFT 1000, you can very easily hit pass, fail, or not applicable to each of those items in that standard. You can save that information, and then you can report it out later if you needed to show that you actually did the visual inspection. Another thing that we do during operations and maintenance is maintenance of our transformers and our inverters. And we can do DC and AC voltage and current testing. We'll test our fuses to make sure that they haven't blown. We can do thermal imaging as well. We can torque terminals. That's not a tool that Fluke offers, but making sure that our terminals are properly torqued is really critical to make sure that our connections don't fail over time. We can do inverter efficiency calculations, which we'll typically do using the monitoring platform associated with the system. And we can do AC power quality measurements, measuring fluctuations in voltage, frequency, looking for harmonics, looking for voltage transient spikes. We can all see those with high quality power quality tools. Now, inverters and transformers need regular operations and maintenance. The manufacturer will provide a maintenance schedule of the tasks that need to be performed and the frequency at which they need to be performed. If we don't do these required maintenance tasks, it may void the warranty. So if we have any damage and they find out that you didn't maintain the system properly or the equipment properly, it may void the warranty. Also, doing the regular required maintenance will prevent failures and ensure our optimal system production. Fluke has a suite of tools to do these type of tests. Basically, at this point, we have a tool for every every single test that we do in the solar industry, from our multimeters and clamp meters, our insulation resistance testers, power quality meters, our multifunction tools, IV curve tracers, even to our network products that can find issues with both fiber optic and copper networks. We have a range of power quality meters that can be used to identify harmonics issues. Another interesting thing with some of our power quality meters is they can be used to conduct load studies. So we can put the power quality meter in place, we can leave it there for a time, we can see how much power and energy a load is using or a load in a building is using, and we can use that data to properly size energy storage systems for backup use cases. So that's a nice feature of some of those power quality meters. Now, modules need operations and maintenance as well. They don't need a lot of it, but visual inspection can find many problems. So things like burnt out connectors, as is shown in this picture. If we have damage to insulation, sometimes you can see that in visual inspection as well. Things like cracked modules, damage to cells, burnt interconnections in the module, those are different things we can see with a visual inspection in many cases. Beyond a visual inspection, using thermal imaging can find a lot of problems that you can't see with a visual inspection. For example, this is a cell that has a problem. I was actually in the field last week and saw this very problem. In the case that I was in, that cell had been damaged for some time, and you could visually see that the cell was burnt out on the front of the module. When you looked at the back of the module, it was the back sheet, it was actually burnt up and charred right where that cell is. Early stages in a problem like this, you would not see that with a visual inspection, but you can very clearly see it with a thermal imaging camera. Thermal imaging modules, the parts of the module or array that are not operating will be at a higher temperature than operating components. And that's because the electrons in the cell are being excited by the sun, and if they don't have a load, they don't have anywhere to expend that energy, so they will dissipate some of that energy as heat. Connections that are high resistance, like module interconnections that weren't plugged in all the way, will be hotter than other similar components under similar conditions. And many times with thermal imaging, we're not necessarily diagnosing what the issue is, but we're identifying problems that need further testing to find out what the root cause of the problem is. With our modules, we can also test voltage and current. We can do operating voltage testing using a set of Y test leads. We can do current testing. Many times with modules, and strings of modules, we're not looking to find a specific voltage. We're really looking for the absence of, we're not looking to find specific current. We're looking for the absence of current. So I've shut my system down because I need to do some maintenance on it or some troubleshooting. If I want to open a non-load break rated disconnect, like a fuse holder or a module interconnection, I always want to put a clamp-on meter on that circuit to ensure that there's no current flowing through the circuit before I open up that non-load break rated disconnect. If I open that device when it's under load, it's going to arc. We call that letting the sun out. That arc is going to damage the connector or the terminal that I'm working on, and it's a safety hazard for the technician. Really important to use a clamp meter before you open any of those circuits. I should also mention that when we're testing current in a solar array, especially with a string of modules or an individual module, we're never using the probes of a multimeter to do current testing, because anytime we put probes on a circuit that's energized to test current, we're short-circuiting that circuit through our multimeter. And as long as the current is below 10 amps, the multimeter will be able to read it. But the problem happens when you lift the probes off of that circuit, you're breaking the circuit, and it's going to arc. It's going to damage the test probes. It may damage the terminal, and it's a safety hazard for the technician. So we're always using a clamp meter like the one pictured here to measure current in a solar array. The tools for inspecting modules, we can use a visual inspection. Using a checklist to make sure we don't miss any steps is really helpful. We can do thermal imaging with either a drone or a handheld camera. We can use multimeters or clamp meters to check voltage and current. Whatever meter we're using to test voltage, especially in a PV system, we need to make sure it has a category 3 voltage rating higher than whatever testing I'm going to be doing. So if I'm on a residential system, I need to have a 600 volt meter. If I'm on commercial rooftop systems, I can have a 1000 volt meter. And if I'm on utility scale projects, you're most likely going to need a 1500 volt meter. A problem that we run into relatively frequently in solar is called a ground fault. The ground fault is an unintentional connection between a current carrying conductor, like our DC positive or negative, and a non-current carrying metal part, like our module frame, racking, conduit, metal junction boxes or inverter cases. There's two main types of ground faults. A solid ground fault is a low resistance connection that is always present. Those are relatively easy to find. Intermittent ground faults, on the other hand, have a higher resistance connection, and they tend to come and go. We may see them when the conditions on site are wet, or, for example, when a tracker moves into a certain position, it may pinch the wire and cause the ground fault. Many different things can cause ground faults, pinched wires, like in the tracker system I just described, or sometimes the wire gets pinched between the module frame and the racking during installation. Wiring can be damaged when it's being installed, or maybe the wire was improperly managed and it's rubbing against a metal part, and eventually that insulation wears away, and now I've got a intermittent ground fault usually at first, and then it becomes a solid ground fault over time. There are two ways to find ground faults. The first is voltage testing on my PV source circuits. That's our circuits with strings of modules. I can test from positive to negative and figure out what the open circuit voltage of the string is. And then I can test from positive to ground and negative to ground. In a system that is off with a modern inverter, there should be no connection between the DC side and ground with the inverter off. So when I test between positive and ground or negative to ground, in either case, I should get 0. I may get some voltage that will very quickly bleed off to somewhat close to 0. That's ghost voltage. As long as it's not stable, I know it's not a real voltage there. The other test we can do is insulation resistance testing. And this is really helpful for finding strings that have intermittent ground faults. I can also do insulation resistance testing on circuits that are de-energized, like our PV output circuit from our combiner box to our inverter, or our inverter output circuit from the inverter to a point of interconnection, or even between different conductors in a circuit to find parallel arc faults. In some cases, I may have an insulation resistance value which is above the IEC standard, which in most cases is 1 mega ohm. But it may be different than other circuits. I've run into this before where I was doing insulation resistance testing on a commercial rooftop system, and all the circuits were exceeding the resistance value of my meter, which was 2 giga ohms, except for one circuit, which was around 156 mega ohms. That is still well beyond the minimum required by that IEC standard, but significantly less than the other similar circuits. When I got out my string diagram and found the circuit, walked the array and did a visual inspection, and I found an interconnection between two modules laying on the roof in a puddle. Not a good way to have your connector. So I took the connector out of the puddle, properly fixed it to the racking, let it dry off, and then retested it, and it exceeded the limit of my meter as well at 2 giga ohms. So that was a good change. Ground faults are a safety hazard. Since there's current flowing to a non-current carrying metal part, I now have energized metal parts in the system that should not be energized. If it's arcing, where there's sparking across the connection, that sparking can cause fires. We see this often in ground-mounted system where the sparks fall down into the grass and then the grass catches on fire. They will lead to arc faults as well, and they start out as arc faults and become solid ground faults over time. You can use any kind of multimeter, clamp meter, or insulation resistance tester as long as it's properly rated for the environment, the voltage that I'm working on. So let's look at some examples of how we can use voltage testing to find a ground fault in a PV source circuit of modules. I got 16 modules, open circuit voltage is around 53 volts. If I measure from negative to positive, I should get the open circuit voltage of the string, 861 volts approximately. If I now measure from the ground to the positive, I should get 0, but in this case I got 645 volts. I'm going to document that, write it down. If I test between my negative and ground, I should get 0. In this case I got around 215 volts. Again, I will document that, write it down. Now when I look at my results, my positive to negative 861 volts divided by 53 volts gives me a module count of 16, which is what I would expect. This is not going to be exact, but it's going to be pretty close. When I divide 645 by 53, I get about 12 modules. And when I divide 215 by 53, I get about 4 modules. What this means is that I have a ground fault 12 modules between the positive and the ground fault, and 4 modules between the negative side of the ground fault, which means counting from the negative side, I've got a fault between modules 4 and 5. Now what I need to do is go out into my array, try to figure out where modules 4 and 5 are, and then do an inspection and see what's causing the ground fault and repair that ground fault. Another example, quick, same set of modules. My positive and negative reading was the same 12. My positive to ground was also 861 volts. Divide that by 53 gives me 12 modules. My negative to ground was 0, which is what I expected. That means there is 16 modules between the positive and the ground fault, and 0 modules between the negative end and the ground fault, indicating that there is a ground fault on the negative home run wire between that last negative module in the string and wherever it goes to, either a combiner box or an inverter. This issue can be very easy to miss because you're used to seeing 861 volts and 0. So when you do the positive to ground reading, you see 861 and your brain may not catch that that should be 0. So just keep that in mind as you're doing this type of troubleshooting. Now, arc faults are another problem in solar arrays. This is a unintentional connection that's causing some kind of electrical arc. There are 2 types of arc faults: a series arc fault, where I should have low resistance, but I have high resistance instead. An example is a module interconnection where maybe they weren't plugged in far enough, or there was dirt in the connection before it was made, or somebody made a bad field connection, made a bad connection in the field. The other type is a parallel arc fault, and that's where I have low resistance between 2 conductors where there should be high resistance. An example would be the DC positive and negative. Maybe they rubbed together and the insulation wore away, and now that positive and negative is arcing and making a connection. I can do a visual inspection to find arc faults where I'm looking for burn damage. I can also use a thermal camera to identify components that are hotter than other components that are similar and under similar conditions, like module interconnections. Here we've got 2 pictures of a module interconnector that were damaged. The one on the top right is a thermal image where that connector is at a higher temperature than other connectors in this system. This bottom one here, there's a little gap here between the positive and negative sides of this connector, so I'm assuming they didn't plug it in all the way. I believe that heated up, and then you had this metal part here making a connection through this burnt out wire here, and that series arc fault here becomes a parallel arc fault as well. So you get both situations in this example. Inverters all have arc fault detection in them, and often they will show an error code and shut off, indicating there's an arc fault. You can do a troubleshooting sequence where you separate certain sections of the array, turn the inverter back on, and see if the fault code still remains. If it's gone away, you know the arc fault is in that section of the array. If it's still there, then you need to isolate a different section of the array and continue that workflow until you find the culprit. Arc faults are a safety hazard. They're arcing electrical connections, so it's an electrical hazard and a fire hazard. Both series and parallel arc faults will continue to arc until they eventually burn themselves out. Thermal imaging cameras, workflows, good ways to find arc faults. In this picture here, this was a module interconnection where the positive and negative side were not fully mated together. So that was a high resistance series arc fault that eventually heated up and caused the connector to burn out. You can see a little bit of the remains of the plastic components. That ended up causing a roof fire on this system. So that was a catastrophic failure due to an arc fault. We're collecting a whole ton of information when we're doing this series of testing. We need to document this information in a way that's easy to record, easy to catalog it, and easy to get it out in the future if I want to review it, and it has to be accurate as well. Having workflows, especially when you get people new to the industry, make sure everyone is doing the testing in the same way and getting the same results. So the testing is not causing problems. We're only identifying issues that have a legitimate cause. Calibration is important with our test tools. Fluke recommends annual calibration for almost all of our products. Read the manufacturer's instructions of your test tool to see what schedule they require calibration. If you're doing third-party operations and maintenance, especially if you're doing testing before the sale of an asset or doing troubleshooting, oftentimes they'll require a certificate of calibration before you start your testing to ensure that you are getting accurate test results. So to summarize, we need to make sure that our test and measurement tools have the proper category rating for the environment in which we are going to be working, either category 3 on the DC side of the system or category 4 on the AC side of the system, especially if we're close to the utility. And it needs to have a voltage rating above the voltage of the system that we will be working on. Fluke has a wide range of tools designed for many different tasks. If you have the right tool for the job, it's going to go faster and it's going to be safer for the technician and give you better results. But we have to calibrate our tools on a regular basis to make sure they're getting proper measurement results. And I didn't really talk about this during the presentation, but it's important to wear the proper personal protective equipment when we're doing testing. Often we are working on live systems, as we see in the picture here, and we need to have the proper equipment to protect ourselves in case there's a hazard. This technician has all the right equipment. They've got fire-rated clothing on. They've got insulated, electrically insulated gloves. They have an arc flash face shield and a balaclava. The only criticism that we have for this technician is he's kneeling, which is not a best practice because that knee touching the ground creates a much easier path for electricity than the insulated soles of his boots. So that being said, that is the end of the presentation. We can take questions now. So if you have questions, please put them in the question box and Katerina will relay those to me and I will answer them.
Thanks, Will. Like he said, if you have any questions, please feel free to put them in the question box and to the right of your webinar controls. We do have a couple questions so far. So is Fluke planning on building a 1,500 volt SMFT?
Oh, that is a good question. That is on our to-do list. So we are looking at developing that. If that is something you're interested in, please reach out. You can email me at will.white@fluke.com and we'd be happy to interview you to find out what features are important for you. At this point, there's a chance, and I'm not going to say this is a definite, but there's a chance that we might actually skip 1,500 volts and go right to 2,000. So that may be where the direction we go. Yep.
Okay. How do the IV curve testers work with bifacial modules?
Bifacial modules are really common in utility scale systems, especially here in the US. The interesting thing about bifacial modules is that the standard for standard test conditions does not include backside irradiance measurements. So when modules are tested under standard test conditions, even bifacial modules, they don't include that. What most people do with bifacial modules is you just kind of expect that the performance factor using the PVA products is going to be greater than 100%. And so it's typically somewhere between 115 and 125%. And people are comparing similar thing. So if you're just testing strings of modules over and over again, as long as it's the same module type, the same quantity of modules in the string, and the same angle and orientation, you can compare those IV curve test results and see if there are any deviations, and that's a good way to find problems with bifacial modules. We do have on the product development roadmap a soul sensor that would be able to measure backside irradiance, that would be able to include that in the algorithm, and that'll probably be in the next generation product as well.
Okay. I've had issues with IV curve trace testing high efficiency modules in the past. How well do Fluke IV curve testers work with this type of module?
Yeah, that's a great question. And I mentioned that a little bit in the presentation. The SMFT 1000 around 19%, actually it's above 19% efficiency, will often throw an error. It's error 14 because it thinks that that inrush current coming from the capacitance of the cell is overload short circuit current. So it prevents that test from starting to prevent damage from the module to the test instrument. The PVA 1500T2 model, when the efficiency exceeds 19%, the current rating drops from 30 to 10 amps. But the PVA 1500HE2 model, specifically designed for high efficiency modules, that's where the HE comes from, can test any efficiency module up to its full 30 amp current rating. So if you're working with modern modules, and most modules these days are above about 20% efficiency, especially the newer ones, the HE model is really the model that would be the appropriate choice. Now, I will say that this issue impacts all IV curve testers, and I've never seen any other test equipment manufacturer discuss, even mention high efficiency modules. So it's an issue with all of the test tools.
Okay,
Great.
we have one more question unless someone else submits a question, okay?
Great.
At what voltage should I run an insulation resistance test on a string of modules?
It really depends on what standard you're working at. Here in the US, there are two standards that have tables for that type of measurement. The IEC 62446-1 standard has a table for calculating the required insulation resistance test voltage. For 1500 volts, they require a 1500 volt test voltage. 1000 volts, it's 1000 volts, and then it varies from there. The ANSI NEDA maintenance testing specifications also have requirements for test voltage. There's kind of a gap in that table between 1000 and it goes from 1000 volts to 2500 volts. So they don't really exactly address 1500 volt systems, but usually you test it around the voltage, the operating voltage, if not a little more. Another thing you can do is look at the in this case, module manufacturers' requirements and see what voltage recommendation they have. It's also very important, I didn't mention this before, which I should have, to check with your module manufacturer and ensure that they allow voltage testing through insulation resistance testing through their modules. Most manufacturers will, but some are restrict that, so they don't want you sending that high voltage signal through their modules. Yeah, is that the last question?
That is indeed. All
Okay.
right, that concludes our time for today. If you would like to receive the NABCEP education credits, please reach out to me via email, which is shown on the screen, to receive the certificate of completion. To find out more about Transcat's products and service offerings, please contact us at 800-828-1470 or on the website at transcat.com. Thank you for joining us today. We hope you got something out of today's presentation and you continue to join us for future Transcat e-learning webinars.
Great. Thanks, everybody. Have a great day.
Bye, everyone.
Bye-bye.